certain level, which is somewhere 12 to 20 ppb limit. Insect cause significant post-harvest losses, which account for 9 to 20% all over the world. Heat of respiration from the grain and molds may cause development of hotspots. I'm not sure, there's some echo coming from the background.
Karan Singh, kindly mute everyone, and I think then Dr. CB Singh will unmute and talk.
Yeah.
Yeah, kindly CB Singh, unmute yourself and then speak.
Thanks, Dr. Matt. So in India, the storage is still a big problem, and it's traditionally storage. These are some of the picture actually I got. I don't remember the source from some presentation. This highlights the issue that I'm going to talk about how we can deal with. So this is the worst form of storage according to the research or the experience from what I have in US, Canada, and Australia. You don't have any, I talk about the stored grain ecosystem. Basically, this kind of environment, you have almost no control on anything, rain, humidity, insect, molds, birds, rodents. So it's exposed to all those factors without any control on or interference on those factors. So grain storage in bin silos or grain bins, it's very common in North America. However, just storing in a silo will not solve the problem. This is an example. In 2016, a canola bin caught fire in Saskatchewan, which is another neighboring province to Alberta, in this bin. So exact cause is not known, but canola is a high oil seed, if you know the canola seed. It's like a mustard, but it has very high oil content of more than 40–45%. So that it has the self-heating tendency. It's heats by itself. And that leads to the sometimes spoilage, and as soon as self-heating continues, it builds on it, and then it can lead to the fire. This is another ethanol plant in US where in this plant they store the high moisture corn for ethanol production, but again that caught the fire. And most likely it happened due to the high moisture in the grain, which leads to the self-heating. Though I don't have any data from these bins how temperature increased, but I do have some of my earlier work when I used to work with this company where they monitor thousands of grain bins. So if you look at this table, from the top, there are different cables and different spatial distribution in a grain bin, where at each, say for example, if you look here, the very one cable, C1 is the center cable in a grain silo, vertical silo, if you visualize in 3D. And that's the temperature shows you. See, S1 is the bottom sensors. Then you move up to 18. That's the top sensor, and they are at 6 feet spacing. And then there are in another ring in that grain bin. You can see here that the temperature in that particular region increased up to 141 degrees Fahrenheit, or maximum was 60.8 degrees Celsius. Rest of the bin is very low temperature. These numbers are in degree Fahrenheit. So you can see somewhere between 10 to 12 degrees Celsius. So this is the issue that could happen to the grain, even if it's stored in proper structures such as grain bins or steel silos. So how we handle with this? Safe storage, how we can safely store the grain without any of these issues. Safe storage refers to the storage of grain for longer period without any significant spoilage. So we don't see these hotspots, we don't see any molds.
Recording in progress.
We don't see any of these issues with the grain, as I highlighted some examples. Stored grain changes physically and chemically due to the different physical-chemical condition, environment, and temperature and grain moisture are the two most significant parameters that determine the safe storage period of grain. So managing temperature and grain moisture are key to the grain management. These are the fundamentals. Obviously, if you have any immature, broken, damaged kernels, unclean grain with a lot of foreign material, that actually increases the spoilage risk and reduces its storability. So these are additional problem that if you don't have proper, clean, healthy grain, then it will have more problem. That means you should not aim it for a longer period. You should have a plan accordingly how long that can be stored, how long you can store it and manage, monitor it. Also, it is very important that safe storage period is cumulative. So it's not that if you had a grain in bad condition, you dried it, you cleaned it, now you have a longer period. If you have it stored for half of that time in poor condition, means that you have, say you had 100, the good condition grain can be stored for 200 days, but 100 days is one in bad condition. That means you are left with only 100 days. You don't have additional 200 days. So that has to be considered when planning the grain management. So I'm going to talk about a smart grain management. What is, we talk about any smartphone, smart TV, smart agriculture is a big word. How do we do with that, use that smart grain management? It's dependent on the same technology. We are using cloud-based platforms for monitoring. We are using sensing technology. We are using modeling. We are using treatment of the grain. But the core is that you are part of the new innovation in digitization in different forms. And we are going to use that. I'll show you how it's being used to manage your grain. So what monitoring that does that, if you have any problem with the grain, you are notified, you are informed, you are remotely able to see it, monitor. You modify, that means if you have hot grain, you have a modification, means you modify those physical conditions, you cool the grain to desired temperature level so that you can keep it safely stored. If you have high moisture grain, you monitor it, then you know what is the moisture. You modifying means you dry it to safely storage moisture levels. Treat it. Sometimes you have insects, for example. You monitor, you find insects, then you apply fumigation, fumigate it, or chiller, whatever method you are adopting, what is more viable, economical for your grain, you use that method, that treatments. Modeling is also part of it, and sometimes it's combined actually with monitor, modify, all these two. It helps you to predict it before actually something happens. So before you monitor, you can see spoilers. Modeling will be able to help you to determine what is the safest storage life, for example. Or modeling will be how long you have to dry, how much fuel costs will be involved, how much energy, electricity costs will be involved for modifying or treating the grain to manage temperature and grain moisture. This is a smart grain management system here. This is vertical steel structure, corrugated bin. These are very common in North America. These are called stool grain bins. In some countries, they're called stool silos, but they are pretty much same. As you can see here, the bottom has a perforated plenum attached to a fan through a duct, and the grain is loaded into a bin. Then fan pushes the air through the grain, and that's how you can dry and cool the grain. It also has these, if you see the cables, they are called temperature and moisture cable. So and that's what I showed in table view, but here you can see here, that's how they're suspended. And the knots, these are the moisture sensors. So it gives you the moisture at different depth of the grain. And there's the multiple cable spatial distribution. So you are able to see localized moisture and temperature. And if the grain condition change, you are able to see localized hot spot, something, which if without the cables, you will not be able to see inside the grain bin. Also, it has an electronic insector that can catch the insects inside the grain bin. It has local weather station. That means it will be helpful in making automated aeration control or drying. So weather station will tell when the grain is warmer or when the air is cooler than the grain, when you can apply the fan, when you can turn on the fan, when you can apply the cooling so that keep the grain cooler, or if you are drying, how local ambient condition or local humidity and temperature are appropriate so that you can dry the grain. Or if you need to add a supplemental heater, low temperature heater to add. Same thing, these are headspace temperature. So if there is anything, any condensation happening in the headspace, because inside the grain is hot, walls are cooler, particularly in North America. Daytime are hot, so head space gets hotter. In nighttime, it's cool. That will cause condensation inside. All this technology, everything. You can use your cell phone. This is all connected to the cloud now, wirelessly, once you have set up. You can be sitting anywhere and you can monitor. If I share my screen and log in here into any grain bin, you should be able to see that data. So you don't have to go to your to the site, storage site, or a farmer doesn't have to go climb into the bin, sniff inside. All this sensor, this technology will help actually monitor remotely. And if there is anything, if temperature goes up, he will be notified by text or by email. And then he can correct it remotely, try to find out by aerating, turning the fan off, or if the condition is not under control, then somebody can go and see. Here, sometimes the distance where the farmer lives and his farm could be 40, 50 kilometers, sometimes 80, 100 kilometers. So it's long distance. Nobody wants to travel, especially in the winter time when the grain is stored and sometimes minus 30 degrees Celsius outside. So, and road conditions are not good. So this technology is very handy here for the farms. This is the same thing on the left side. There's a grain bin in Australia when I was working at University of South Australia on a project that we did on aeration. These are another grain bins. It has a local weather station. Right side, you can see that how the technology works. So inside or the moisture cable that connected, the cables are connected to the cable node, as you can see here. The cable node is wirelessly connected to a gateway, and gateway is connected to the cellular modem, or yeah, that's how, and through the connection, wireless connection, that data from the gateway is thrown into the cloud. And from the cloud, you can log in and see from anywhere. So there's no restriction. Also, when you use your phone and turn your fan on, that gateway will send that command to the, if you look at the right in your left side, there's a fan node, if you are able to see. Fan node radio. So gateway connects wirelessly to fan node radio. Radio send that command to fan nodes, and fan node has already a control developed into it based on different conditions and considering local weather data, grain moisture. And then it makes a decision whether fan can be run or not at that time. If the condition change, fan will turn off. That information will be sent to the gateway. From the gateway to the cloud, you will be able to see any time, almost in real time. So this is the advantage of technology. So I mentioned that this is what can be done. So why monitoring is important, grain monitoring. Stored grain is always at risk of spoilage due to self-heating, condensation, mold growth, insect infestation. All these things will result actually in increase in moisture and in most of the cases in increase in temperature. As soon as you see a change in temperature, means something is, it's good, and same as for human being. When we check our body temperature, it is up, then we think something is wrong. So same thing with the grain. If you see the increase in temperature, so, but you don't want to go and monitor in real time by climbing to the bin and then assessing the site. You can do remotely, as I showed you. Moisture of grain, moisture temperature, insectivity, CO2 level, and phosphate, vital to develop best grain management practices. This is how you can make sure that your grain is in safe conditions by looking at the grain condition and then treating, modifying if required. Monitoring not only ensures safe storage, but it provides early warning. As I say, that you see the temperature increase, then you mean that you have to dry or cool the grain, or worst case, you have to sell it or move some other places. Also, this monitoring ensures that your fan control, aeration fan is effective. So if you're monitoring, you know that temperature is changing, the grain is cooling, or if you're drying, the moisture is reduced over a period of time. So you know that, yes, your control is effective. If no change, that means it's a waste of energy. The fan is 10, 15 horsepower, fan is running without any positive desired outcomes. This is some of the data. So I talked about the technology that we have. That I showed earlier, how we can. This is how I took a screen capture from this cloud-based OP platform, grain management platform. You can see here that bin 1, it has grain type that you enter, current grain maximum temperature, ambient temperature, average grain moisture, ambient equilibrium moisture content, fan mode, it's off. What we did here that on the right side, that's when the grain was filled actually. So grain is, right now it's a summer in Australia. So this is time, the grain is actually in late November, December is the grain when it's harvested in summertime. Sometimes it's up to 40, but in this case, the maximum grain temperature that came on the top was up to 36 degrees Celsius. So as we know, anything over 15 or 20, so this was pretty dry grain, no issue with the moisture, it was very dry. But insects love the hot environment. The 26 to 30 is the optimum for insect growth. So this is perfect. If you don't do anything, then you will have big problems, insects in this, and that's a major problem in Australia for the grain storage. So what we try to do, we try to cool it using all this technology and remotely. It's about from where the campus is, it's about 2-hour drive, 150 to 200 kilometers from there. So we don't go there every day, but we are able to see the conditions in real time almost. And after running the fan for 2 months, not regularly. The fan is smart control, automated. Anytime when outside is cooler than the grain, then only the fan will run. Okay. So this, we were able to bring it down to below 20 degrees Celsius, most of it. And this is for Australia. In North America, our recommendation is to bring it down to 3 to 5 degrees Celsius. But that's not possible. Here, why we want to bring it down, to have the mold control, which needs to be cool. Insect, anything below 20, its insect activity is reduced. And if you are able to cool below 15, then actually reproduction is stopped. So this is still good. That's another monitoring example here that one pharmacy sent me this. These are the lines are how the different sensors in the cable I mentioned earlier at different depth. So this is over the period of time. The grain was source sensor 1, 2, 3, that's the bottom sensor. If you consider different layers in a grain silo in 3D visualization, sensor 1 is the bottom layer, next, sensor 6 is the top layer. So sensor 4, as you can see here, rest is fine. It started to, the grain is up to 4 sensors. So sensor 5 and 6, they're out of the grain. So don't consider, but sensors, the highlighted, the bold red one is the actually top sensor in canola. So you can see here, harvested 26 degree, freeze within 8 days, 30 degrees. So slightly increased 4 degrees, but within next 4 days, actually, it climbed 10 degrees Celsius, just 4 days. So that's the indicator. The farmer who has this technology, he realized he moved the grain actually from that bin. It was a smaller bin without any cooling. But when he moved in that time, it was already below 0 degrees Celsius. So he was able to cool the grain. And then he stored that grain up to June 15th next year. And he was able to sell it at 8.4% moisture without any fine or any, as a number 1. So the grades here, how it's traded, they are number 1, 2, 3, 4, 5. 4, 5 are basically, they cannot be used for food consumption. 1 is the top grade without any quality defects, including the moisture. This is another hot spot that you can see here. If you visualize from the starting, you see a big spike all of a sudden. So that's the self-heating. The grain has high moisture, started respiration, and that building of that moisture added heat, and then it climbed. This is from the US, so that's why it's in 138 degrees Fahrenheit, but it's about 60 degrees Celsius. So they had the fan here. They were able to cool it down to 60 degrees Fahrenheit, which is about 10, just over 10 degrees Celsius. So that's why this monitoring is very, very important for any, I personally, I would recommend anyone who is storing the grain in grain silo must have temperature monitoring at least. I would prefer both temperature and moisture, but must have temperature monitoring. This is again, in the same way, you can see that in a table view that certain area got actually really bad in that, and then they had to cool it down.
Recording stopped.
So what are the modification I talk in that plot? That
Recording in progress.
Modify. Dry and cool grain is the key term for the safe storage. It's the key, fundamental for the grain management. A crop can be harvested as soon as it reaches physiological maturity and can be dry. So in field, for example, you can store the wheat at 12%. You don't have to store it, harvest at 12. You can harvest it 15, 16, and then dry it down to desired moisture level. In-bin natural air drying is considered the low cost and high quality in products. So what in-bin drying is that the fan is attached to the grain bin itself, the storage bin, and the storage bin is kind of a drying system also. And using the natural air, slowly you dry the grain if you have right conditions. Then drying, after you finish the drying, then you cool it, then keep it for a longer period, up to 6 to 8 months time. This is the same example that I mentioned earlier, but South Australia, that we used aeration. In this, the grain silo that you see, the center is moisture cable. These are the sensors at different depth level. So that sensor, the values are shown on the right side, initial values, left side after you complete the coding. But in 3D visualization, if there is anywhere bad grain, you know where the problem is, or what is happening to the grain. And you can track it all the time using 2D plots. Same thing, as I mentioned, that you can look into all those sensors, those cable data from each of them in this plot. So you can see start at 40 degrees Celsius. Over the time, they cool it down to nearly 20 degrees Celsius. The solid green light shows when actually the fan was running. So if the conditions were good, the fan would run. If the conditions were not good, the fan would stop. But it shows when the fan was actually running at that side. The blue line shows the ambient conditions. So you can see when the fan is running means that ambient is cooler than all those solid color lines, and the fan was running to cool the grain. This is another example of rice drying. So these are different layers. You can start the bottom layer, top, second, third, and the top layer. But you can see that how the moisture was reduced over a period of time. Started with the bottom layer, started first drying, layer-wise drying, the second layer, third layer, and the top layer. So they started almost 20% moisture, and then they were able to dry it to 14% target moisture, which is appropriate for milling rice. In this study, what we did, I was involved in this study. We compared with using smart automated fan control and also using the manual control. So manual means that you start the fan on, let it run 24/7. So we compare that. This is that the target was 14, and you can see here everything within 0.5% moisture content. Whereas in this case, when they use the manual, they over dried. So it's a loss because they are selling weight based on the weight basis. So they over dried 1%, and they have thousands of tons. So if you say they have about 1 million ton storage, but even if 1,000 ton storage, 1% loss, weight loss will be a lot of money. So that was a big benefit for this company to move from manual control to automated control. And each blocks, if you can see on the left side, is 1,000 tons, each one. So there is a huge storage facility. Currently, I'm leading a province-wise state-wise study on-farm grain storage, grain drying, and energy efficiency. This is a farm that part of it I visited. You can see how big is the operation. This farm here, it has almost a little over 14,000 acres of storage, more than production of wheat, barley, canola, and storage. So in this study, we are looking at improving on-farm grain drying using in-bin system, high temperature drying system, combination studies. And as you can see here, these are different farms that we are working with and collecting the data over a 3-year period to come up with the recommendation for improving the energy efficiency in bin drying and storage. Next is mathematical modeling I mentioned in that diagram. It's a powerful low-cost tool to predict the safe storage of the grain. So as you can see that these are the big bins. If a grain bin is 1,000, for example, if $1,000 canola bin, 1,000-ton canola bin, and it's around $20 per bushel. So any huge, you need at least $500,000 investment to try. And if you fail, it's a huge crop loss, huge value. So it's not easy to do these experiments. Whereas through the modeling, we can create those conditions and then run simulation to see what will happen. And then we can do once we know that, yeah, these are good, reduce that risk, and then we can validate. That's what we did in Australia. Several models have been developed to predict the grain temperature, moisture, and intergranular gases composition. So it's a major field. A lot of work has been done in the past. However, a comprehensive modeling approach considers the geographical location, structural type, commodity, cumulative storage conditions, all these factors into it. So generalized model is needed, not one unique specific condition. That's what the requirement is, so that it can be used anywhere, in any condition. Considers both aerated and non-aerated air. So models have been developed to run the aeration fan, but what would happen when the grain is sitting without any aeration? So it has to be combined both. And also, most of the model, we use some fancy programming language or some coding on our own C, C++, Java, whatsoever, okay, or even MATLAB. How the farmers are going to use it, they are not programmers, even though they are smart. So we need to have easy tools. We build those tools so that we have that computation, web-based, easy to use and interpret by user. So we are working now with some industry partners where the basic modelings actually, they just enter their grain information, they enter the zip code, and then we have API integration. It automatically picks the nearest weather station, weather data, and then uses grain, everything, and runs simulation. Just tells the farmer, yeah, you good to go, red or green. You can run the fan or you don't run the fan. That's it. So these are the kind of tools that we need, and we are working in developing those. We are also using CFD modeling for the sum of the work. It's a modeling tool to develop robust and flexible mathematical analysis of heat and moisture transfer model during the aeration process. It's based on finite volume methods, can accurately represent the inherent fluid flow properties, its thermophysical transfer phenomena taking place between the air and the corresponding grain volume in the stored bulk. Investigate also CFD application in the grain management. We use it to investigate the effect of geometry and location of aeration system in an on-farm grain structure. So aeration system, some of them, if you're not familiar, it's called full floor perforation, where all the floor is perforated, while in some it's a V-duct or some structures that don't have the complete perforation. I'll show you in the next slide. So we need to come up with how we should design them. What is the efficiency of aeration, uniform aeration? So uniform means that all the grain in the grain bin receives sufficient amount of air. That's a heat carrying or moisture carrying model for the grain bin. So this is what we try to do in this. Also investigate the required number of hours to cool or dry the stored grain depending upon the region. It's a time bound. Safe storage, grain has a limited storage and it's cumulative, I mentioned. So make sure that we are able to calculate the time. We make sure that it's all the control, they are done before the actually significant spoilage happens into the grain. So these are the tools that we are using. This is a brief overview of finite volume methods, and one of my PhD students, Subham, he worked on this simulation work in his now research associate back in my training in Lethbridge. So you can see that here it's divided, the whole grain bin, 1,000-ton grain bin is divided into different small elements, and this area is more uniform as we have hexahedral element. tetrahedral element on the top, on the cone section with the nodes as defined here on the axis. And then we apply the PED model with FEM support to have discretized linear equations and develop solution methods, which are converged approximate solution. So this used to optimize element size, what size it should be, optimize solution method for a specific purpose. So we also found out what method is more appropriate, and optimize time steps to capture thermophysical behavior. I mentioned here this paper that we published in drawing technology. If you are interested, you can see this paper later on. These are some of the outputs that we got. So I mentioned that airflow is very critical. We want to make sure that all the grain inside the grain bin is cool has. So you see that that's a static pressure distribution. And the bottom one is, you see, the airflow is not uniform. If you can see, there are dead spots. Dead spots is the darker blue area that has no almost or very negligible airflow rate. So if you run the fan in this condition, then this area will not be cooled. So if you have insects, you have the mold problem, they will just multiply. Same thing in the bottom here, in these corners, those areas not receiving sufficient airflow. So that's why we need to have a proper aeration system design. Just building a grain will not solve the problem. You need to have sufficient airflow, uniform airflow, monitoring, control, and have a best management practice to ensure the grain is safe. This is also I mentioned that airflow is not uniform. So this is a 1,000-ton, 42 feet diameter, 33 feet EU height grain bin. And in that grain bin, we actually measured the airflow rate on the top at different locations. You can see here. So since the grain is peaked here, the center has almost zero airflow rate, because the distance from the bottom to the top is more. So air takes the path of least resistance or less static pressure. And that's why in the sides, you have more airflow rate, less into the center. So if you run the fan, heater, everything, that's why the center will be your high risk zone, or how the spoilage will happen there. So in that model, we use that 1,000-ton silo and also 100-ton upper bottom silo, these two types of silo, and computational domain with optimized element size, what element size should be used. And since here, if you see on the right side, these are the blue portions are the ducts. It's not full flow perforation. And that's where they're connected with the fan. So we use a different element size to capture that, where the variability is more, capture that information. Where it's more uniform, then we use a different element size. But we were able to optimize them and use into the model to come up with those results. So these are the work that we have done in the past, and we are trying to improve and use in some other crops such as sugar beet storage. So this is the outcome of the simulation for heat and moisture transfer. On left side, these are initial conditions, and then we ran the simulation for 48 hours, and then these are the final conditions, how the change. So you can visualize layer-wise change and also see in 3D. So this is my summary for the talk. A post-harvest grain losses can be significantly reduced by smart grain management technology. Grain handlers can make informed decisions to avail the best marketing opportunities, increase profitability through quality optimization, moisture control, energy savings, reduce operating costs, detection of contaminants such as molds, mycotoxin, and prevention of spoilage. I would like to thank all the funders for my previous program at University of South Australia, SAGIT, Grain Research Development Corporation. They were funding my appointment at the University of South Australia. My current funders are listed. They are part of my research program. They're funding infrastructure as well as some of my current projects in grain drying, sugar beet storage, potatoes, variety trials. These are my project collaborators. I'm working at the moment for my research at the college. Thank you.
Agarwalji,
Thank you.
yeah. Now we
Thank
can.
you, Dr. Singh. Now I invite our director, Dr. Mehta, to say.
No, we
Give
can
his
have
opinion.
one or two quick questions.
Okay. Let
From
us have
participants, even number of participants from CFET, including directors. CFET is also there.
Yeah. Nachiket sir is also there. I welcome him.
Dr. Singh, I have a question. What is the spacing, usually the spacing between the sensors, the moisture and temperature sensors in the big science silos?
Yeah, so it's a very hard question to actually answer to me, honestly, because grain is a poor heat conductor, So it takes a lot of time to move that hotspot, localizes hotspot change in temperature to another location. But we are limited by the load because you cannot have so many cables. Their cost is expensive a little bit, and also the load on the roof. So industry uses actually 6 feet spacing. That's what the sensor to center spacing is, about 6 feet as is standard. That's the commercial cables, moisture cables they use. So each cable will have, vertical cable will have 6 feet spacing of the sensor, temperature and moisture sensor.
Anybody else has any?
Yes,
Sir,
I just wanted to compliment Dr. CB Singh, number one, for a very good presentation.
Thank you.
To tell him that this type of work has already been initiated in CIAE for some time. And a few of students of Dr. Devbandya, they have done this type of work, but not to this scale. And working on the scales that Canada and US or Australia are working, that probably is not economical for us. So that is a different issue. But the later part of your presentation was very interesting, in the sense that that is the area where majority of our scientists and students are not very well exposed. Use of CFD and these type of things for design of storage structures. One of the major issues that comes to us is availability of software with expertise, and number two is computationally challenged. So I was wondering if you can consider conducting a workshop for the scientists and students of both these institutes, even Cft Ludhiana and some other institutes under the Agriculture Engineering SMD of ICAR will also like to join. So conduct a workshop of maybe 1 or 2 days, 3 days, to let people know that how these things can be implemented. Number one. And another thing is there in your university or organization, is there any possibility of conducting these things collaboratively? Because it is computationally challenging. We don't have that type of hardware available with us, and not everyone can have. So if some facilities are there for sharing of computational spaces, or some cloud-based solutions are there which people can use. So if you can cover all that workshop, it will be. Thank you.
Thanks. Yeah, so I agree on the second part. That if there is any opportunity for me, I have capacity. I have research associates, my team has to work on or some other form to work with you or anybody who is interested. Time could be a factor, so I need to know ahead of time and plan accordingly. Usually until March, it is a little bit okay, but then April, May, June, our harvest season starts. So June, July, August, September, though 4 or 5 months are very, very busy. I won't be able to do anything. But before that, I might be able to do that. Yeah. I agree that computation resource infrastructure is an issue, but fortunately we have that capacity at the college, so we will be able to do that certainly. The first part, I was reading a news somewhere in India that India is moving towards the silo storage. And they want to have since the government is that, or FCIR directly, they are building huge, they call it 12,500 ton silo, huge silo, and 50,000, 25,000 ton storage capacity across India. So you can imagine that I showed you 1,000 ton silo, if it's 10 times bigger. How much risk you are carrying if you don't have expertise, you don't have people who are expert and the condition who can work on those conditions to minimize those risks. So I think that's the area that I think should be considered, if that's the plan for the government of India, FCI, to store the grain in those silos.
Dr. Rajkumar, I think he was telling something.
Hello.
Yeah, please.
Sir, good morning. I'm Dr. Rajkumar, Professor and Head, Department of Food Process Engineering from TNA, Coimbatore. It's indeed a very good presentation. I would like to know whether this in-bin drying, the same concept can be extended for drying paddy, and what may be the condition for extending the same technique to paddy actually.
So when I showed in my presentation, nobody calls here it rice, but actually that was a paddy drying. So
Yes.
my own experience, that data from the paddy drying was from Australia. In Canada, we don't have good condition for rice, so there's no paddy. But I have worked in the US, in Arkansas, that's the major rice industry. Most of the drying they do in the in-bin drying system. But if it depends on the condition, I don't know what condition. If you have good dry air in those conditions, but in tropical, that the issue is that you have very high humidity. So if you are in 90% humidity zone, or if you are most of the, say 50% of the day, you are in 80% plus humidity, then it will be a challenge. Then you need a heater. You will be able to do, but then you use low temperature heater.
Thank you. Thank you, sir.
Asrar, here.
Yes, sir. Good morning. Sir, I am Asrar from Cft. Sir, I wanted to ask, sir, as you said that India is now trying to move towards huge silo storage. And we in India have a very peculiar problem of infestation, insect infestation, particularly in the temperate tropical regions. I wanted to know that, sir, whether this smart storage, smart silo storage, are there any hindrances towards fumigation, incorporating fumigation system into the smart storage structures?
So what type of fumigation you are?
Sir, fumigation with very hazardous fumigants like phosphine, aluminum phosphate.
Yeah. I've not covered that part, but yes, there are companies, they are selling those technology for the to monitor fumigation so that it's uniform. In general, fumigation works very well in the grain bins. It's not a problem. So, and that's quite expensive to my knowledge, that technology. And I don't see additional value. What I want to see is that if you have alternative, just monitor temperature and see that if there is any insect activity, that if you see any increase in temperature, and if you keep it cool, then you can minimize that. Rather than in Australia, fumigation is very common. Every farm, every grain bin is fumigated 2 to 3 times. But what happening over the years now, that they have a high resistance for some of the insect species is there. So they are trying to look for some alternative than the fumigation. Does that answer your question?
Yes, sir. So I also wanted to know the lesser hazardous fumigants, for example, carbon dioxide. I tried at a smaller level in my own lab. So whether carbon dioxide fumigation, is it feasible for large storage systems?
No, not really, because it's the issue is the volume we are handling. You can control in a small bin, but when you have 1,000 ton, I mentioned that I read somewhere in India, they're building 12,500 ton storage bin. It's such a huge bin that you will not have any control. You will not be able to make uniform distribution. I tried with a very small silo and it did not work. Basically, the idea was to kill the insects with that. So it will not work at a smaller scale. You can sell smaller bags or something will definitely work, but not the scale that we are talking here.
Okay, we may take last question from Dr. Ravindra Naik. He has already
Sir,
put
good
his
morning.
question in chat box.
Good morning. These days, a lot of work has been reported through CFT modeling. How accurate are these models in respect to the real data?
So using say 100 kg grain and just a small cylinder, probably you will be within 0.2% here in moisture or 0.5%. What we did, that our study was, I think, not sure how many others similar study on actual 1,000-ton silo. So we were within 1%. So that's quite reasonable number.
Okay, sir.
And this has changed in, just to add, this computation has actually, capacity has been increased dramatically in last couple of years. So that's how it's a faster computation, it can carry more burden, and that's why these models are improving now.
Okay.
There is a question for how much depth the insectors to be installed in smart silos.
How many?
For how much depth the insectors are kept? Please see the chat box. Probably he wants to know up to what depth of silo the insectors has to be installed. Insect catcher.
Insector. Okay. All right. So insector in general, the insects, again, those are number companies are giving. It's not that you can install everywhere. They're expensive. There's one company that makes OP. They have a pattern that 10 to 12 or 16 same way pattern as you have cables. What they do is they use some modeling. So based on that certain location and grain size, volume, and then they convert what will be the insect density per kilogram. So that's how that works. In general, they tend to stay at the top. So research has suggested that they are not underneath the grain, couple of 6 to 8 feet, probably maximum from the top. So that's why their distribution is at the top. They are installed, and that number of insects, their distribution, grain volume, and then there's a modeling in the background that converts those actual number of insects, actually the insect density into the grain, a number of insects per kg, and that information is being used when to do the fumigation. That's the purpose.
Okay.
If no more questions, then I invite Dr. Mehta to say a few words.
Thank you, Dr. Agarwal. So first of all, I thank Dr. Chandra Singh for agreeing to deliver talk at such an odd hour, and that also on one of the important area in which government is also putting lot of thrust on smart grain management. Your presentation was informative, and it has created curiosity among our colleagues also. So I thank for that purpose also. And one of the important area we have observed that we have already initiated working in this area, as mentioned by my colleague Dr. Nachiket Kotwaliwale. But our scale of work is on lower side. So we need some guidance as well as support also for scaling up of whatever research work we have initiated in this area. And in that, he had proposed that we can have workshop. You have also agreed for that. So we think that we will plan to have one workshop before March with the approval of a council. And we will initiate from our side for that purpose. And we will require your support for organizing that workshop. Another point I would like to mention that government is also putting lot of trust And for that, they have created Agriculture Infrastructure Fund. And under that, they are providing subsidy to entrepreneurs, those who are putting the grain storage structures. So in that, there will be need for moving towards the going for smart storage structures with the use of sensors, so we can monitor the infestation of the grains inside the storage. So these are some points particularly about your talk, and we are thankful to you from the side of the Central Institute of Agriculture. We are also thankful to all our colleagues from the institute, as well as our colleagues from the Central Institute of Post-Harvest Engineering Technology, including Dr. Nachiket, as well as our number of friends who have participated from different state agriculture university, and a few participants maybe from abroad also. So we thank them for participating in good number in this talk. Your talk is informative as well as interesting. There may be number of questions we may not be able to take because it's of time limitation, but I suggest my friends to send their queries, and we will transfer those queries to Dr. C.B. Singh, and he will try his best to answer those queries. Thank you.
Thanks, Dr. Mehta, and thank you everyone for participating and attending my talk. And I'll be very happy if you have any question, please do reach out to me.
Thank you, sir. Now I'll invite Dr. Devbandya Mahapatra for formal vote of thanks.
Thank you, sir, for giving me this opportunity to propose vote of thanks. On behalf of ICAR-CIAE and on my personal behalf, it's my great pleasure to present the vote of thanks for this event. A heartfelt thanks to Dr. Chandra Singh for accepting our invitation to deliver a talk on grain storage management. He's been very supportive and very enthusiastic whenever I asked him to deliver a talk. Thanks, Dr. Singh, again. My thanks goes to our director and mentor, Dr. C.R. Mehta, who is instrumental in conducting the webinar. He is always supportive. And also I thank Dr. Karan Singh, who is always there to host these online events. Dr. Adinath Kate for his effort to communicate this message to everyone. But last but the least, I give my wholeheartedly thanks to all the participants from ICAR institutes, different state agriculture universities, both faculties and students whose presence has made this event a great success. Thank you all. Have a great day, and a good night to Dr. Chandra Singh.
Thank you, Deva. Thank you to Dr.
Thank you,
Singh.
sir.
Thank you, everyone.
Thank you to Dr. Nachiket also, Director CFET, for participating. And I thank you to all. Thanks. And just close it.
Recording stopped.